Hello, welcome back on another lecture. Today's topic is on maximum likelihood as well as kernel density estimation. Professor Wu, let's get started. So previously, we learned how to obtain the P of x, right, for several distributions, namely by recognizing what the shape looks like. So this was a normal Gaussian distribution, uniform, categorical. So by recognizing these situations and remembering the equation associated with them, you can go from data to the probability distribution P of x. Okay? And with these equations that we have seen, it turns out that the equation was simple enough and we got really lucky. Basically, we know ahead of time what the theta value is. So for the exponential, right, minus theta x, P of x. So for this equation, right, in this particular example, theta is simply 1 over the expectation of x. So if you know the average value, which if you have the data, you can just average it, you essentially know theta as well. So a lot of these equations that we have seen, finding the theta associated with the equation is not that difficult. Okay? Well, that's great for simple probabilistic equations. What if we have something that's much more complicated? Well, when it gets a lot more complicated, finding theta becomes very difficult, okay? Because you can't just like take just like know what theta is, right? It's not necessarily the average, and it may not be the standard deviation. So for these cases, when you have an equation that is really complicated and you don't know what theta is, how do we go about solving them? That is the topic for today. And the most standard way is called maximum likelihood. Maximum likelihood. This is how it's traditionally solved. Okay, so independent variables. We previously talked about the concept of independence, and independence came from basically conditional probability. So this was the equation for conditional probability, where x probability of x given y follows this equation. Right? From the conditional probability, we know that we move this over here, then we know that the joint is the marginal times the conditional. And we talked previously about how if if x and y are independent of each other, right? If y has nothing to do with x, therefore it doesn't matter what y happened, the probability of x doesn't change. That implies that y is independent of x. And when that's the case, the equation for independence becomes this. So notice how you even given y, x doesn't change. Therefore, this is equivalent to p of x. Therefore, when you have the join is equal to the product of the two individuals, that implies that you have two variables that are independent of each other. Right. The reason why idea of independence is important is because when we collect data, right, we've also previously talked about this, we really want to assume that the data is independent and identically distributed. Means we collect maybe 10 samples, each sample came from the same distribution. Okay? And that each person is independent. Like if you're collecting blood pressure from 100 people, then you want to be able to assume that person 1 and person 45 have nothing to do with each other. Like the blood pressure of person 1 should not influence the blood pressure of person 45, for example. So this is called the IID assumption. And in order for us to kind of continue to do what we are doing today, it is very important that we keep track of this independence as well as the equation for independence. The equation for independence is if you have two variables or three variables, the equation is that they simply multiply with each other. Okay, so let's say now we have a Gaussian distribution. This is you can collect samples from this, right? So let's say we're using Gaussian distribution to model 1,000 samples. So we want to collect 1,000 samples all from this Gaussian distribution. The probability distribution for Gaussian looks like this, which we have seen before. Okay. Now, given that we are collecting 1,000 samples, then the first sample we're going to call x1, second, all the way to the thousands. So there are 1,000 samples. Then the probability of each distinct event will be probability of x1. Notice how we put x1 here, right? So probability of x1, and then probability of x2, then we put x2 here, and probability of x3, x4, so on and so forth, all the way to the probability 1000. So now we have the probability distribution for all 1,000 samples. This is sample 1, sample 2, all the way to 1,000 samples. So notice that we can get the probability of each event by plugging x1, right? So what was the probability of the first event? So I previously mentioned that whenever we collect samples, one of the key assumptions is that the samples are independent of each other, independence, which we call IID. If all 1,000 events are independent of each other, then the probability, the joint distribution for x1, x2, all the way to x,000 is therefore simply probability of x1 times probability of x2 all the way to the probability of 1,000. Okay. Another way to write this is with a product, looping from 1 to 1,000. Right. So it's multiplying x1 all the way to 1,000 together, multiplication. Since we don't want to write 1 to 1,000 every time, we're just going to write x, right? That x implies a vector from 1 to 1,000. So when we talk about p of x, we're talking about this whole thing. This p of x is a product of 1,000 Gaussians multiplied together. Okay, so this is the distribution. This right here is the distribution. Okay. Now, what we need to do now, remember, we need to figure out what mu and sigma square is. Well, previously, you know what mu is, which is the mean, and you know what sigma square. But remember the premise of what we're trying to do. What we're trying to do is we're going to assume that we don't know. So assume this is a simple example, but let's assume we have a very complicated equation and we don't know what mu and sigma square is. Then how do we go about finding them? Okay. Well, let's say we make a guess. Okay. Let's just make some guesses on this. Well, if we picked a very, very inaccurate guess for mu and sigma square, which together is called theta, if we picked a really, really bad one, okay, we pretended, therefore, that means a bad choice of theta, and that our distribution must be way off. So if we this is the data, and if we picked a really bad number, notice how our equation does not fit to the data at all. They're actually pretty far away, right? Ideally, you want something like this, but instead we have something like this. So this is telling you that your prediction is way off. Okay, so so if that's the case, then what would P of x1 be? What would be the probability of first sample? Well, it's saying that if let's assume this is the bad guess you made, right? If you made a really bad guess, and this is the first sample right here, it will say that the probability of first sample is 0. The probability of second sample is 0. Like all the samples given this probability would be close to 0, right? One more time, let me say this in a different way. If we claim that the Gaussian distribution looked like this, which we made a guess and it was a bad guess, then the events that actually happen, let's say this event, according to distribution, this distribution will be very unlikely, right? This event will be very unlikely. This event, so every single event will be very, very unlikely, right? So px1 for the first event will be very small. Px2 will be very small. In fact, pxi for every single sample here will be basically very, very small. And as a result, if you have px1 times px2, a small number times a small number times a small number, all these small numbers multiplied together, it's basically saying p of x is equal to basically zero, right? So, so you can see here that if we made a very bad guess for mu and sigma, then the probability x, the joint probability will be very, very small, because when we multiply all these numbers together, it'll be small number times small number times small number. So from this we see that a bad choice of theta leads to a very small joint probability, very, very small value. Now, what happens if you pick a better one? So this was the bad one. Now we picked a better one. It's not perfect, right? This would have been perfect, but this one is better. Now, when it gets better, what happens now? Well, x1, previously, x1, probability of this x1 would have been 0 according to this distribution. But according to this distribution, x1 is a much larger number, much, much larger, right? So x1 is quite likely. Right, so is x2, so is x3, x4. So probability of x1, x2, all the way to x thousand, every one of these numbers will be significantly larger. So a bigger number multiplied by a bigger number multiply a bigger number, then p of x, the joint distribution, must be a much larger number as well. So this observation basically tells us that the better mu and sigma we pick, the larger the joint distribution, the more likely that these events actually happen. And from this, we see that, therefore, if we find a theta in, mu and sigma in this case, then it leads to a larger and larger and larger value of the joint distribution. Okay? The idea of maximum likelihood came from this observation. And what we want to do is, let's say over here, we have the mean and the standard deviation. So all we have to do, here's the joint distribution, right? All thousand of them multiplied together. What we want to do is find the theta 1, theta 2, which is these two values, that maximizes the joint distribution. And that's actually it. Like, if you just maximize this, find the theta 1, theta 2, which we know how to do. You can do gradient descent. You can use closed form solutions. Okay. So I actually wrote the code to do this, and I'll show you the video. It looks something like this here. So you can see, if I press play, I'm running gradient descent on this like objective that we just saw. And you can see that little by little, it's maximizing the joint likelihood, implying that like you're getting a better and better and better prediction. Okay. So I'm going to pause this. Let's continue. Okay. All right. So this is the code that allowed me to generate that. You can check it out when you have the chance. All right. In summary, if you have some data with a specific distribution p of x, okay, if you don't know p of x, but you can essentially recognize the equation, then that would be the easiest way to go. However, if you have the equation, but it's a complicated equation, then you want to use maximum likelihood to find the missing parameters for the equation. So simple equations are easy. You just need to recognize them. Harder equations, you use maximum likelihood. Okay. And when we do use maximum likelihood, when you want to maximize something, remember, when you're maximizing or minimizing something, you can take the derivative and set the derivative to 0. If you can actually do that, then that's great. Like, then you're done. So If the function allows you to do that, that's what you do. And that gives you the closed form solution. Take the derivative, set it to 0. Now, if the function is complicated, then you will need to use gradient descent, right, to approximate the parameters that you need for the equation. So remember, in the beginning of the semester, we were looking at functions of machine learning algorithms. So therefore, you see this Gaussian maximum likelihood. So this is the one we just did. But for exponential, for Bernoulli, for uniform distribution, all of them, you can actually solve them via maximum likelihood. Right? So far, like you should have an idea of what these equations mean. You know L1, L2 norm. I think you guys have done the linear regression, and these are all components that you have seen already, as well as this one. Okay. All right. So that's, I believe, it for part one. I will see you in part two.